So now we're going to apply HOR logic to verify our first program, which is the swap program in all uppercase. And swap swaps the variables A and B, so it swaps their contents using a temporary variable called T, right? So we assign A to T, B to A, and T to B. But you know, when we do that, it's easy to mess up, right? And end up not swapping, but you know, having twice the same value or things like that. At least I've messed this up before. So we're going to use HOR logic just to make sure that we don't mess it up this time, right? So this is the HOR triple that states correctness of swap. So first we declare two variables here that say that store the initial value of A and B. So we call them A0 and B0. Those are pretty good names, I think. I'm rather proud of myself here. And we have the precondition that A equals A0 and B equals B0. And this is necessary because the trouble is, it would be tempting to say, oh, we start in an arbitrary state, right? Lambda is true. And then we say, well, in the final state, we end up, you know, A equals B, but somehow in the initial state, and B equals A, but again, somehow in the initial state. And that is exactly the problem. We don't have access to any other state except, you know, the one we're looking at here. So we cannot refer to the initial state. So that's why we have this trick of having, they're called logical variables in HOR logic. But again, it's just a phrase you have to take at face value, because we're in Lean, we could say, you know, S is a logical variable, right? We're in the logic and it's a variable. But it's just a concept. That's how they're called in HOR logic. So these variables freeze the values of the initial state, right? So we get them here, and then they stay stable for the rest of the execution of the program or verification of the program. And this is what we want. Okay, it's an idiom we're going to see over and over again. So we'll probably need a bit more space. So we look at this HOR triple here, and we see, well, of course, we could rewrite the definition of swap if we wanted. And I don't know why that part is so slow. And then we see, okay, what we have is an assignment, right? Sequential composition. So semicolon here. So we're going to use sec intro, and actually sec intro prime is the friendlier one because it generates the goals in right order. And now we have three goals. The first goal is you have the first assignment, the second assignment. Did I say they're in the right order? Well, I'm not sure. It depends on how you define right. But anyway, this is how this proof is written. Let's put it this way. Okay, right. So it's the right order because we continue with the rest of the program, and we'll come back to the beginning later. Beginning is here. This is the rest of the program. And that means we can focus on the second semicolon here, again with the same command. And now we've broken the program down to three parts. So you have the assignment of T here with A, and then you have the assignment here with A, and then you have the assignment to B. And what you have is also some conditions here which are not filled in, right? So we know the post condition here, we don't know the precondition. Here we know nothing is the one in the middle. And for the first one, we don't know the post condition, but we know the precondition. And these variables are connected, right? So when we fill one of them, then we'll also fill the other one somewhere else. However, and this is a very important warning here, here is the place where I think Lean is really stupid. And I hope, I hope the main developer of Lean is not watching me now, but this is extremely annoying and shameful, because you would expect that the M1 here is connected to the M1 there. but actually I think it's connected to the M2 and so on and so forth. So there's a connection deep inside the code of Lean, but when the things are printed, the names are generated on a pair sub-goal basis, which means you always start at M1 at the front. M1 comes before M2, M1 here, M1 here, and then you lose this connection or even confuse the users. So this is just terrible, but we'll live with it. We're not going to think too much about these connections across sub-goals anyway. We're going to focus on one sub-goal at a time, and these variables will get filled in automatically. Okay. So what do we now? Well, we just have an assignment here, so we're going to use assign intro. And what's happening now after this? Well, we have, well, it's gone, I think. Is it gone? We had 5 goals, which is, of course, we did assign intro, and then, we didn't know before what the precondition was, but now we do, and that variable is gone. And now the same thing will happen again. We're going to start with this post condition, and assign intro will find out what the precondition is supposed to be, right? And then we have yet another assign intro here, but this time, you see, we don't have a variable here at the front. So if we try assign intro, things are not going to fit syntactically. But the version with the prime is very nice because it has this linear pattern that can match anything. And then it leaves us instead with a horrible proof obligation. And it turns out we can easily kill it by using a so-called contextual simplification. So if we just do simp, then it shouldn't do it, unless Lean has become much better than it used to be. It doesn't work. I mean, you get quite far, but the problem is that you have, this for all, this, all this stuff. So you have to say intros. Right? And then at this point, I think if you do CC, then it's done, or simp, something like this, then you're probably done as well. But instead, we can also say, do contextual rewriting. Was it the TT? Yeah. And contextual rewriting means exploit these implications, right? So when you have an equation on the left-hand side of an implication, use it as a rewrite rule on the right-hand side of the implication. So, and I think it doesn't do that by default just because it's afraid of entering loops or being too slow. But it's a very useful feature which we're going to use over and over. Maybe we've used it already, I don't remember. Certainly don't remember talking about it this year, but what does that mean? And here's an alternative proof of the same Hoare triple. And this time we just use the definition of Hoare logic of Hoare triple. So the first thing we do is we just introduce, all the for all and the premises that we get from the definition. And then we reason directly, in terms of this big step semantics. So we do a bunch of cases and so on. And at the end we use our, favorite new tactics. So here I think contextual simplification didn't do the trick. Don't ask me why. But finish did it, right? So after some time you get used, oh, let's try finish, let's try total. You get some intuition also as to which one works. And if nothing works, then you break things down like I did above with the simplification here, right? Where I did a bit of simp, a bit of intros, and a bit of CC. So what I'm trying to show here is that Hoare logic just provides a convenient means to reason in terms of semantics, but you could also reason directly if you wanted. In this particular case, there's no big gain of using Hoare logic. So Hoare logic really comes into its own when you have loops, when you have while loops and invariants, because doing the same manually here would involve doing an induction. Whereas with Hoare logic, you don't have to do the induction. You just have to dream up the right invariant. And that's usually less cumbersome.